Hey everybody, welcome back. Today we're going to talk about torque and Newton's laws in rotation. So there is such a thing called translational inertia, and that's measured in mass, in kilograms. All it is the resistance to change in translational motion. It wants to sit still, it doesn't want to move anywhere. Or if it's moving, it doesn't want to speed up or slow down. Now there's a rotational equivalent. It's called rotational inertia. It's an object that doesn't want to start rotating. Okay, it's a little bit harder to figure out. The rotational inertia is I, and that's the sum of the mr squared, and it has units of kilogram meters squared. So if we take a look over here, we have a person that has dumbbells in their hands, and it's easy for them to twist back and forth. But if they stick their arms out wide with these dumbbells, it's much harder for them to twist back and forth because they have the same exact mass, but their radius where the mass is located is much farther out, so therefore they have much harder time rotating. They have a much larger rotational inertia. So here's our question: which has more rotational inertia for these two objects? And we can easily see that it's the bottom one, B, but we can actually calculate what those values are. So you take the mass and multiply by the radius squared for this one as a radius of d over 2, and add them up, and we get md squared over 2. If we repeat the same thing for object B, we get a rotational inertia of 2md squared. And I want you to notice that when we double the distance of the mass from the pivotal point, that we quadruple the rotational inertia because it's related to radius squared. So here are some common shapes that you'll need to be aware of: a hoop or a ring, a solid disc, a solid sphere all the way through, or a hollow sphere like a basketball. Notice that the ring, since all of its mass is out of the radius, is got a 1 up front. So it's completely effective at producing inertia. The farther the mass it gets, the larger this number gets out front. We also have a thin rod rotating about its center of mass or rotating about its end. Notice that when it's rotating about an end, it has more mass farther out, so it has a larger number out front, a larger factor than when it's rotating about its center of mass. So here we go. The following figures, we have 3 identical mass objects, and they all have the same height. All are rotating about their centers as shown. Can you rank them from greatest to least rotational inertia? Well, obviously the ring must be more than the solid disc because it has all of its mass out at the end. But then this picture frame has these corners that are farther away with a larger radius than, say, the radius of this ring. So it should be C, A, B. Now I want you to notice where the center of mass of all these objects are. Center of mass is in the center of these discs, in the center of the spheres, and in the center of the rod. All objects will naturally rotate about their center of mass. If you want them to rotate about a different spot than their center of mass, then you have to put an axle in there, like this rod. If we throw it in the air, it won't naturally rotate about this end. We'd have to pin it down and put an axle through there to make it rotate about the end like this. All right, so now let's talk about torque. Torque is a force that's offset from the rotational point. That can either be the natural rotation point, the center of mass, or a fixed axle rotation point, like for this wrench. Notice this foot is applying a force this direction, and it will produce a torque around the rotational center of mass. And force A will produce a torque that will also be clockwise, as will B, but the torque from B will be larger than A because it has a larger radius. C is at an angle, but it still will produce a torque that's clockwise. And D will not produce a torque at all because its line of action goes right through the pivot point, so it won't make it rotate. It would be just like this football being kicked right through the center of mass, and if that happened, it wouldn't rotate. So how do we calculate torque? Well, torque equals the perpendicular radius times the force, or the part of the force that's perpendicular to the radius. So let's look at this one first. So here's our force C alone. Notice how it's at an angle, and it has a part that's perpendicular to the radius, and it has a part that's parallel to the radius. The parallel part will not produce any torque, only the perpendicular part. So we have to calculate the perpendicular part of the force, multiply by the actual radius, and there's our torque. Or a more ingenious way to think about it is to think, here is our force, and here is the line of action of this force. In geometry class, the distance between a point and a line is always a perpendicular radius, essentially. That's what we have here, a perpendicular radius. So this perpendicular or minimum distance between this point and the line of action is our lever arm, perpendicular radius. And if we multiply that by the force, it's the exact same number. We've got a square board here that's got a pivot in the center. We have 4 forces, all the same force. Which ones of these produce a torque? C, we can see, goes right past or right through the pivot point, as does B, so they don't have a lever arm. So these two will not produce any torque. A will produce a torque that's clockwise because its pivot point is here and its perpendicular radius is between here and here. And D, but notice it has a radius that's longer. It will produce a larger torque. So D produces a larger torque than A produces a larger torque than B, and C, because they're both equal. Now, will the board rotate about its center? So just like if the force to the right is bigger than the force to the left, then we will get a net force to the right. So we have a net clockwise torque. So yes, sorry, a net counterclockwise torque. And so yes, it will rotate counterclockwise about this pivot point. So here we have a pulley that's attached to a string wrapped around it and has a pivot point in the middle, rotational inertia I, radius R, force pulling down F. Will it rotate? If so, which way? Well, that's really easy. It's going to rotate clockwise because there's our perpendicular radius and we get a clockwise torque. Calculate the acceleration. The sum of the torques equals I alpha, and our torque is the radius times the force since they're perpendicular, and we just solve for alpha. We have a 10 kilogram pulley that's in the shape of a uniform disc, and it has a radius of 2 meters. They have a string draped over the top, as shown in the figure. One side's pulling down with 100 newtons, the left side's pulling down with 40 newtons. What is the acceleration of the pulley? All right, so this one is producing a clockwise torque. The 40 is producing a counterclockwise torque. So we have fighting torques. So clockwise minus the counterclockwise torque will equal the rotational inertia, and this was the rotational inertia of a pulley as shown in our diagram earlier, and that equals alpha. And so if we just solve for alpha and plug in our numbers, we get an alpha of 120 radians per second squared. Let's take a closer look at free body diagrams. So take a look at all of these free body diagrams down here and decide whether you think they're in equilibrium or not. Now, be careful. We have 2 types of equilibrium to consider now: translational equilibrium and rotational equilibrium. Let's consider translational equilibrium first. Okay, so on our first free body diagram, we have a force to the left and right. They're equal, so the sum of the forces in the x equals 0, so the acceleration will equal 0 in the x direction, so no acceleration, it's in equilibrium. In B, we have mg down and we have a half mg up on both sides, so the forces all add up to 0 in the y direction, so it's in equilibrium. In C, we have a force up and down, but the force up is greater than the gravity force down, so it's not in equilibrium. This one will accelerate with a y direction upward. Same with this one. There is an unbalanced force up, and so this one will accelerate upward. This one right here, there's a force up and a force down. They are identical, so the acceleration equals 0. The forces in the y direction cancel out, so it's in equilibrium. Now, these last two, these get a little tricky. We're talking about the center of mass. The center of mass of this object will accelerate up. The center of mass of this object will not accelerate. For our last one, we have an unbalanced force up, and this one is pinned on the left end. And it will accelerate upward. The sum of the forces in the y do not equal 0. All right, now let's look at rotational motion. So we don't have an object per se here, so there's no way for us to find out what the radius is for these forces. So we really don't know what's going on with the torque. So this is really important for free body diagrams when we're talking about torque. We must have a free body diagram that has the object shape in there and the force is attached to it appropriately. So otherwise we can't tell what the torque is. All right, so here's an object that has a center of mass here. There's a force through there. There are no other pivotal points as far as we can tell. And so this force will not produce a torque because it's straight through the pivot point. These are both identical and they have the same perpendicular radius on either end. So the sum of the torques here is 0, so alpha will be 0. It won't try to rotate. This one as well, the sum of the torques is 0, and it will not try to rotate either because these forces go through the pivot point. Now this one, it's going to accelerate upward translationally, but it will also rotate omega because, alpha, because it has a torque about its natural pivot point. So it will have an alpha counterclockwise. This one right here, it will not try to translate. So the center of mass will stay put, but this force is going to try to rotate it. This force is going to try to rotate it. And so both of these are in the same direction. So we're going to have an alpha counterclockwise. Now look at the difference between these two. This one will not, the center of mass will not move, but it will rotate because the forces up and down cancel. This one will rotate and move upward. Okay, the center of mass will translate upward, where the center of mass here will not move. And this one right here, since it's pinned here, it can't move about this point, so we have a torque about that radius and that force, so we're going to have a counterclockwise alpha again. Here we have a compound pulley. That means we have two different radii. So this one, the outer one is 7R, the inner one is 2R. We have a 3 kilogram or 3M mass hanging down off the right, off the larger end of the pulley, and we have a 10M mass hanging off the smaller pulley on the inside. So will the thing rotate? Yes or no? And if so, what direction? And calculate the acceleration. And then what is the direction of the net force on the system? So here's our pulley. We have a 3 mg pulling down on the right. We have a 10 mg pulling down the left. Now this one is going to produce a clockwise torque. The one on the left is going to produce a counterclockwise torque. They're going to fight each other. So I decided to name the clockwise torque positive and the counterclockwise negative to keep them separate. And when we take the perpendicular radius times the force, we get 7R times 3 mg, and we get 21 rmg for the clockwise. That's from this one. And then the 10m is going to give us a 20 rmg. And so, hey, this one wins. So it is going to rotate. It's going to accelerate clockwise. We can figure out what that acceleration is going to be using Newton's second law for rotation. So I have a positive clockwise torque and a negative counterclockwise torque. And then I is given, our rotational inertia as 50 mr squared, and I plug that in here. Lots of things cancels, the m's cancel, one of the r's cancels, and I'm left with g equals 50r alpha. Solving for alpha, I get g over 50r. Notice the units come out correct. So that's going to be radians per second squared. The next question is what's the net force on the system? This mass is going to be descending. This mass is going to be ascending. So that means the center of mass of our system as a whole is going to be rising because we have more mass that's rising than more mass that's descending. This one's going to go down, this one's going to go up. So the sum of the forces equals ma in the y direction. Since our mass is going to be going upward, accelerating upward, we need to have a net force up. Where does that force come from? Well, that force comes right here. We didn't draw this one, or I didn't draw it in my free body diagram. There's a force here, upward, on the axle. And this force upward must be greater than, what is that, 13 mg, so that the net mass of the system will ascend. Describe the motion of a meter stick that is hinged at the right side and released. Well, that's really easy, right? If we hold it here and release it from the other side, it's going to rotate this way. All right, now draw a free body diagram. Explain the motion of the meter stick using your free body diagram. Which is greater in magnitude, the weight or the upward force at the hinge? Justify your answer, and then calculate the initial angular acceleration of the meter stick when it's released from the horizontal position as shown. Here's my free body diagram. There is a gravity force acting through the center of mass, and since there's no forces left or right, then the hinge only needs to pull directly upward at this instant. Now, why does it move this way based on our free body diagram? Well, this force acts through our pivot point, so no torque. This one is producing a clockwise torque this way, so therefore we're going to end up with a clockwise acceleration at this instant. Which one is bigger, this one or this one? Well, I've drawn this one smaller. Why have I done that? Well, if we take the sum of the forces equals ma in the up and down direction, I want you to notice that the center of mass will be descending. So therefore it's accelerating down. That means that the gravity force must be bigger than the vertical force at the hinge. And what will that acceleration be for the meter stick as it falls? Well, torque equals I alpha. Our torque is the radius, which I just called this radius L/2 for the length of the beam or the meter stick. The force is mg. This is a rod that's rotating about its endpoint, and so from our table earlier in the video we saw that that's 1/3 ml squared. Solve and we get 3/2 g divided by L, and that's clockwise rotational acceleration. Now let's take a look at rolling without slipping. First thing I want you to understand is that there must be friction. If there's no friction, then an object will just slide across the surface and there won't be any torque and it won't try to rotate at all. So here's an object on a flat surface. You can see that there's a gravity force down, there's a normal force up, and there's a friction force to the left. Notice that I've drawn them at the point of contact. Gravity comes from the center of mass, normal and friction come from the point of contact. Now, when this tries to rotate, omega, as it rolls to the right, then there has to be a torque to make it rotate about the center of mass. And the normal force and the gravity force cannot do this because they pass right through the center of mass, the pivot point, so they don't have a lever arm. So there's no torque from them. So the only one that's producing any torque is the friction down here. The same thing is true on an incline. When you put an object on an incline or a ball on an incline, it's going to try to move down the incline and it will roll clockwise in the picture I've drawn. We still have a gravity force straight down from the center of mass, and the normal force is still from the point of contact and will pass straight through the center of mass because it's perpendicular to the surface. Neither of these can still produce any sort of torque. So if there's no friction to act through this radius, then the object will simply slide down the incline without rolling or rotating at all. So we need this friction in order for it to roll without slipping. The last thing is, if it's rolling without slipping, that friction is static friction because there's no sliding. For our rotating object on a flat surface, in the x direction, we have a friction force to the left, which I've called negative, and that should equal ma. So this object, even though it's moving to the right, should be accelerating backwards in the negative direction. For rotational, notice that we only have one torque, and that is, I'm going to call this a radius r, and that's perpendicular to this force. So we have one torque, which is r times F, that's force friction static, equals I alpha. That is the same thing we get over here when it's on the incline, because nothing has really changed. It's the exact same setup for the torque. Acceleration down the incline is a little bit different though. We have a component right here, mg, if this is theta, sine theta, pulling it down the incline. But we have a friction force against it up the incline, and that equals MA. All right. I want you to notice that since we have this term right here, the friction force, that means that this object, this rolling object, will go slower down the incline than an object that just slides down. If there was no friction, if that was zero, then it would slide down faster because this would be zero, and we'd have a greater acceleration. Okay? So a rolling object down an incline goes slower than an object with no friction that just slides down the incline. We've been talking about Newton's second law in rotation. Now let's talk about Newton's first law in rotation. So an object at rest will stay at rest. So an object that's rotating will also want to keep rotating. So let's take the one where the object is at rest. That's static equilibrium. All the forces must cancel out, but also all the torques must cancel out. So whenever you have a situation where an object is sitting still, all the torques anywhere on that object must cancel out. So be sure to draw an accurate free body diagram and be wise about where you pick your pivot point. You can choose it wherever you want since it's not rotating. And if you choose it where some forces cross through, then you'll eliminate their torque from the equation. Just make sure that all the clockwise and counterclockwise torques always add up to be equal to each other and cancel out. So here's an example. We have this beam and a weight on the end and a cable that's holding it up, and there's the pivot point here at the end. So calculate the tension in the cable and also the reaction force at the hinge. So here's my free body diagram. I've got a 2 mg down for this mass. The beam has a mass of m, so I got an mg down through the center of mass here. I have a tension force up along this cable, and I have a vertical component and a horizontal component. These two are alternate interior angles, so that's theta there. So this is T cosine theta, and this is T sine theta based on this angle. I don't know what's going on over at the hinge, or do I? The sum of the forces in the x direction equals 0. Since we only have two forces in the x direction, T sine theta, which is to the left, then the hinge must push to the right, and the hinge force must equal T sine theta. All right, let's look at the y direction. We have T cosine theta upward, and downward we have an mg plus a 2mg, and then we have something going on at the hinge because that's probably pushing up or down. I'm going to assume it's pushing up. That seems like the most likely to me. By the way, if you don't know, just guess, and then at the end, if you got it the wrong direction, you'll come up with a negative force, and you know you just have to flip it to the opposite direction. So I have a vertical force up and the T cosine theta up and then 2 down. Now, I do not know what T is yet, and I don't know what this force is yet. So I got to move on. We'll come back to that. Let's look at the torque. The torques must also add up to 0. Now, most of us would pick this point because that's the actual pivot point, but I'm going to encourage you to pick this point on the far right. And the reason why is because the torques must cancel everywhere. And if I pick this point, I'll eliminate two torques, the torque from the 2mg and the torque from the tension. And all I'll be left with is a torque from the gravity force for the weight of the beam itself and the vertical force from the hinge. So the sum of the torques equals 0. This one is torquing it, clockwise. So this one must be torquing it counterclockwise. So it looks like I guessed correctly. And this one has a length of half the length of the beam, and this has a length of the full length of the beam. So that means this vertical force must be half the size of this one. So I get length over 2 is the radius times mg is my torque for this one. And that must equal the torque for this one, which is Fv, but it has a radius of L, so the L's cancel. So that means Fv equals mg divided by 2. Nice. So we know the vertical force. Now that we know that, we could plug that in here. So I'm going to move that around over here. And so I get T cosine theta plus the vertical force, which is mg divided by 2, equals this, which is 3mg. So if I take this and subtract it from the other side, I get t cosine theta equals 2.5 mg. So the tension equals 2.5 mg divided by the cosine of theta, and that's our answer for the tension. Nice. And we could take that and then plug it in up here and get the horizontal force. So our horizontal force would equal this, 2.5 mg times cosine theta divided by, times sine theta divided by cosine theta, which gives us a tangent theta. And there is our horizontal force. Nice. This problem, we have a ladder that's leaning against a frictionless wall of science. So derive an expression for the normal force from the floor on the ladder, the normal force from the wall on the ladder, and the frictional force between the floor and the ladder. Here's my free body diagram. I have a gravity force down, mg. I have a force from the floor up, that's capital F for floor, and then I have a friction force because the ladder is going to try to slide this way, that's small f here for friction, and then I have a force from the wall. All right. Well, first of all, this is static, so the sum of the forces in the y have to equal 0. Therefore, mg must equal force from the floor. This one equals this one. And then the sum of the forces in the x have to equal 0. So that means, hey, this one has to equal this one. The force from the wall has to equal the force friction from the floor. Can I tell the relative size between this pair and this pair? Well, I can use torque to figure that out. I've got a pivot point right here that I'm going to assume. And if you'll notice from my diagram, this mg comes down this direction. So its radius is right here. That's the radius for the mg. And then if we look here, the force from the wall goes this way, and this is its radius. Notice how its radius is much larger. So therefore, since those are my only two torques about this point, that means the force from the wall must be smaller than the gravity force. So if we were to rank these, mg would equal the force from the floor, and those two would be greater than the force from the wall, which equals the force friction. In order to find out the actual size of the wall force compared to mg, I would need to know the size of this radius compared to this radius so I could throw it into an equation. Finally, there is a rotational equivalent to Newton's third law. So just like forces, for every torque, there is an opposite pair. When two objects act on each other through a torque, they'll exert torques on each other in opposite directions. So for every torque, there's an equal but opposite direction torque. A prime example of this is a helicopter. So here you see the helicopter rotor is being rotated or torqued counterclockwise. This will produce a opposite torque on the fuselage, which will be clockwise. And the fuselage will want to go clockwise around. So in order to keep that from happening, we have to have an outside force to cancel out the clockwise torque on the fuselage. So here the tail rotor produces a force to the right through this radius, which produces a counterclockwise torque, which balances out the clockwise torque on the helicopter fuselage so the fuselage doesn't spin around. All right, everybody. That has been a very long video. Congratulations for staying with it. I'm proud of all of you. You're doing great, and I'll see you next time. Bye-bye.